So similar to what Leo did a while ago, you just need to open that link, and then here you have a short README where you will find some of the explanations that you will need to use this code. Here is a link to the pre-recorded version that you may want to click after. So there is a YouTube video of about half an hour explaining step by step all the code. And here is some links of the API sources that we'll use to download weather data. So if you just go to the code button here and then click on download zip, you will download your file. I already have on my machine. And let me go over it, because here we have also some I have a very short publication explaining what this code that I'm going to share does. It's basically using 3 main sources of weather data that they are available in R through APIs. So the idea is to put them together and retrieve and also calculate some variables that you may need for crop modeling purposes, if you need, for example. The 3 main sources that this code tackles are DayMed, which is a refined version of NASA Power, which is another of the sources. DayMed is only available to North America, Canada, United States, and Mexico. Daily resolution, and is the one that has the best resolution with 1 square kilometer. The 3 of the sources they were data from the 80s and above until the present. Normally, they will have a kind of a month or 45 days lag to get the latest data, but it's pretty much from the 80s to present. So NASA Power is instead of in contrast to DayMed, is available globally, but the resolution is much less, detailed, with about 50 square kilometers instead of 1. So if you are going to use a data set from the US, which is most likely, I would recommend to use DayMed. However, there may be some variables that are available in NASA Power that they are not in DayMed, and etc. And finally, this code also brings you part to download data from CHIRPS, which is mainly data from precipitation. This is in the case that if you want to use a data set that is outside from the US, and then you're looking at better resolution for precipitation compared to NASA Power. It's about 5 square kilometers, so it's very good. And here you have some of the links to the corresponding GitHub repos from each of them. Here you have DayMed, the DayMed R, which is the API we're going to use. This is NASA Power. NASA Power and CHIRPS, they are both belonging to the R Open Science project. So they are very well checked. Okay, so now let me go ahead and go directly to the code. If you download your file and then you unzip that, you will find a structure like this. And the same like what Leo did, you need to click on the R project file, which is this one here. We're going to open that. I think that I have it open. Let me close this. And I will open from scratch. So were you able to download this zip file? Yeah, good. Okay, so within the zip file, you will find a couple of different files. The one that I want you to open is the R Markdown file, which is called Agromet 3.0. And that one contains all the code organized in different sections, from section 1 to section 5. Section 1 is basically how to create an input data set, which is in this case creating a table, a data frame, which has the minimum requirements you will need to retrieve weather data. So what will you need is an ID or the name of the site or number. If you want, you will have details of the crop, the name of the location, whatever. But the most important ones are two, which are latitude and longitude. Following this system that Leo was mentioning before, the GWS 84, which is kind of is one of the most common. Which is basically the in a decimal format. Okay. So here is an example how we generate two of the files that you have. You have two CSV files out there, and this is how we are generated. We're creating R if you want to create R, but if you want, you will have your input from an external source, which could be a CSV file or an Excel file, whatever. Besides that, you may also need to add some dates, key dates. Mainly, you need a starting date and an end date to retrieve the weather. In our example, we have, for example, an ID number 1, which is corn. Let me open this. I will run all this. If you're familiar with Markdown, you will have all this code organized in chunks. So you just press this green play button and it will run the entire code block. So let's open one of these. So let's see data frame inputs. This is basically what we created. It's a data frame which has several columns: ID, the name of the site, latitude, and longitude, the format I was mentioning, and then we have a starting date and some other dates that it could be important for your database. Let's say that you have flowering of a crop or seed filling dates, whatever. But most likely you will have at least a starting date and an end date to retrieve the weather. If you see here, for example, we are retrieving for a corn crop, we are retrieving data from April 25th to September the 30th. And for wheat, for example, we may retrieve that from October 15th to the next June. So with a data set like this, or an Excel file like this, or CSV, you will just be able to retrieve the weather. Let me go this is how we create the files. If you're using R, it's writing a CSV. And then in the next chunk, this is similar to what Leo was showing before, that sometimes you may have the data or the dates in different formats, with an underscore or with a hyphen or with dots or whatever. So if you want to tell R that that's a date, you need to transform that as a date and tell this is a format. So in this case, using an underscore, we are telling the year coming first, then the month, and then the day. So that's what we do here. So then we create a table like this, right? And then you will transform as a date. So if we go now to data frame input, now you see that you have this format with a hyphen, which is basically the transform version. Let's go. I'm going fast with this because this is just how is the input that you will need to retrieve the data. Similarly, you may want to create or get a database that is historical. For example, if you want to retrieve data from several years at once, so you may retrieve data from, I don't know, January 1st of year 2000 to December 31st of the 22nd, right? So that's also possibly with this. So now in section 2, if you follow the outline here on the right side of the code, you have how we will create the different functions that we need to retrieve the data, because each API is having different formats or different ways to download the data that they don't necessarily match. It's the same with the units. They don't necessarily match with what you may need. And here I'm defining just some examples of solar constant or radiation that may be useful if you want to create a reference about transpiration, for example, that any of the APIs will provide by default. So I'm just creating these variables because we're going to use them later. And then you have in line, let's say in line 189, you have the definition of a function to retrieve weather from day met. And here you have all the code, and I'm not going to go into detail on this, but basically we're creating a function where we have an input data frame, which is the one that we created before, which could be the input for a single season or a historical one. And then you have a variable that we call DPP, that is days prior planting, that is mainly for agronomic purposes if you have a period before the sowing of a crop. Normally the default is 0, so you are not going to use it, but if you want, you have the option. And then there is a bunch of lines of code where we are transforming some variables, renaming to have a more, probably a naming system that I'm more that is more friendly to me, at least. And then here you have some, for example, this is a formula how to create a reference about evapotranspiration. You have all the details in a PDF that is on the documentation of this code. And basically you need to run this chunk to create a function. It's not going to do anything rather than creating the function, okay? It's just doing that. And then on the next line, we will use that function. So where we have the data frame, whether they met, and then we call the function whether they met that we created in the chunk, in the previous chunk, and then we specify the input, which is equal to this file. So basically we are going to download weather for 3 different locations with different dates, each of them. And then we are going to use this variable days prior planting. So let's see how it goes. So we just press enter, and here you may see on the console, that is going 1, 2, and 3. So it downloaded for the three of the locations. If you have 4 or you have 20, you will run that number of times. And then you may check with this package that is called scheme, is basically to explore the data set. It will run and create a summary of all the different variables that we created. So let's see how the data frame looks like. So you may see that for ID number 1, which is the location number 1, for a corn crop, the cycle Scandia, this latitude and this longitude, we'll have the day of the year where we started collecting the data, and then all the consecutive days, after that, where we are collecting all the data. So we have the day of the year, month, and day, the date also. So we have all in different formats. And here you have, for example, the day length, precipitation of those days, radiation, maximum temperature, minimum, BPD, mean temperature, reference evapotranspiration, and then we are also creating these variables that they are extreme precipitation events, which is assigning a number 1 if you have a precipitation more than 25 millimeters in a single day. And the same with the extreme temperature events, we will record a 1 if you have temperatures above 33 Celsius on a single day. But here we're just having all the daily data. So we have day by day, but we are not creating any summary. So the idea of this code is that we may also use that to create summaries. So we have the day met, the function and how to run. We have the same for NASA Power. In the case of NASA Power, I will ask, you will check for all the different APIs, but NASA Power, once in a while, it uses to change the name of the variable. I don't know why. They found better names or whatever, but they are changing. So in the latest version, they changed the name of precipitation, for example. So I put a file within the files here that is explore NASA Power HTML, where if you open in a web browser, it will show you all the different variables that NASA Power has. We retrieved that from the package, and you may see that it has kind of more than 100 variables with a daily resolution. And in the case of precipitation, it's called this, for example, is preg.core, something like that. So they are changing the name. So it's better that if you once in a while you check, you may retrieve and check what are the names of the different variables. So let's go back to the code. So for NASA Power, we can do the same. We could run it very quick. So here we'll create a function. And here there is a important detail for NASA Power that, for example, it doesn't have a vapor pressure deficit by default, but you may create that using the saturation, right, of the air. So there is a formula that I put somewhere there to create a VPD, for example, here, you see? That is basically the difference between the saturated and the actual of the air. Is the same. Is doing exactly the same that where they met. And again, we may just run it. It will be very quick. Not in the case of chips. Chips, many times the server, I don't know why it uses to fail. That is pretty common. I'm getting a lot of comments and questions with that. So let's see how it looks like. So for example, you may see that this is the daymet the one we download first, and let's compare, for example, I don't know, the column here, precipitation and radiation for the first row. We have here you have precipitation, and then you have radiation. You see that they won't exactly match. They won't exactly match because the resolution is different, right? So they may be similar, but not necessarily. But for both, you have daily resolution for all the different variables. So you also have as I told you, you have the option for chips, that is just precipitations and related variables. I'm not going into detail right now. So I will jump to the section 3, which is creating different time intervals that you may be interested in. If you are interested in the single season of a crop with interval that is basically summarizing the entire season, you may create, the different days from the start and the end, but it will be a summary of the whole season, of the entire season. You may create intervals that they are even in days, so you may have 30 days intervals, so you may divide the season into that, or you may divide the season in equal intervals. You can do with a code like this. I'm not going into detail. And then you may also have custom intervals that if you have specific days, as I was mentioning, I don't know, if you have phenology like flowering, seed filling, probably you won't need it for this exercise of the hackathon, but you may have the option there. And then finally, this is how you create a summary, right? So in the summary, you need to put the input, which is the data we downloaded previously from daymet, that it has the daily weather information. For example, here, the DF weather daymet. So we may put that as an input, and then we define which type of intervals we're going to use. So here again, we are creating the function, and in the function, we are creating, for example, the sum of extreme precipitation events. We are creating the growing degree days, crop heat units, the sum of radiation, the mean temperature, the sum of precipitation, the duration of the interval in days, the Shannon diversity index, which is how is the distribution of precipitations. You have a bunch of different. So this is just, again, creating the function. You may add your own formulas if you want. And then we may run those summaries. For example, for the summary they made, we'll use that function that is summary they made on NASA Power is the same. And then we may use the input, which is the weather data frame with daily data. And then you specify which type of intervals. In this case, we may say, okay, we want custom interval. So we may just run that, and then again and again. So here we may have, let me show you the summary. So instead of having all the daily, now you have a summary per different interval you have from, I don't know, pre-planting to flowering, flowering to seed filling, and seed filling to maturity. And then for the location number 1, you have a summary of each of the variables, precipitation, temperature, etc., for each of the periods. Oh, I'm going, so let me go here. So the same with NASA Power, you can run with the same functions. You will just change which is the input, the data frame here. So we may take a look also. And this comparison is easier perhaps. So you may see they made that you have the duration, it should be the same for each of the intervals. So you see that that's not changing, but then when you have precipitation, it may change because the resolution is different, as I mentioned before. Still, they may be similar, but with some differences. And besides that, you may also want to create, and probably for this exercise, it could be more relevant, historical summaries. Instead of going to a summary within a season, you may want a summary of across the years, you may want to identify anomalies, etc. So in a very similar fashion, you will have the function of retrieving the weather data for example, here the data frame historical, which instead of going season by season, we just ask for the same location data from 23 different years in this case. So here we'll retrieve that data with an enter, and then you see that it's pretty fast. For the 3 locations, you already got the data. And then you may explore the data to see if you have empty variables, whatever. You might have a bunch of different. You may do exactly the same with the NASA Power. So let's see, it may take a bit. Let's see. Oh, maybe I will stop that. But you can run it. Sometimes NASA Power may take a while to run. The same with chirps. Chirps, it may take a while, since if there are different years, you may expect some delays with respect to the met. And here there is some explanations on how you get the summary, but you may have options, because you may get a summary by year, or you may get a summary by the month within each of the year. So here is 2 functions to just get the interval from the same data that you have. From the historical for each year, it will retrieve the month and or the years that you want, and then from that it will going to retrieve or summarize the weather. In the DayMed, for example, you may create years DayMed that it will be using that function historical years, specifying the database. It just have the daily weather data for each of the year. So let's run this, for example, and here we may create this summary. Oh. Here is the summary. For example, you may see for location number 1, we have for the year from the year 2000 to the 22, from January 1st to December 31st, or December 30th, depending on the year. If the year it has a 29 days in February, will retrieve until 30. I don't remember exactly why, but it will do that. And then you have the summary, sum of precipitation, exactly the same that we did before for the season, but for each of the years. In very similarly, you can do the same, but year and month with no problem. You just need to specify here. Oh, sorry. You will just need to specify here what is the data, how you do that. So we may run that pretty quick. Let's see. And then see, may take a bit. There you go. And then the same, but you will see that you have year 2000, month 1, 2, 3, 4. So we have all the years expanded month by month. So this is a way that where you can get all these weather variables with this. And we can perfectly do the same for NASA Power. Here is because we didn't retrieve that before. But you can do that perfectly for both chips and NASA Power as well. Sorry if I went up pretty fast. But the code, basically, you don't need to do much. All the functions are created. So basically, you just need to run. And if you want to create an extra variable, you can go to the functions and add a variable there. Or you may send an email and ask me a question. I will be more than glad to help. But yeah, I mean, we've been using this. I created this code in 2020, and we've been using our group. I mean, most of the students are using this because it's pretty easy to get the data and get summaries.
Adrian, there's a question in the chat.
Oh, yeah. Oh, yeah, very good question, Leo. Yeah, I mean, Leo is asking if the crop heat units take into account the crop species. Yeah, in crop heat units were mainly developed for corn. So now the code has the variable for corn, the same with growing degree days, using a base temperature of 10 Celsius degree. So if you want to use another crop that it has a different base temperature, you may just go and change it. Yeah, thank you. I haven't gone to that. Go.
Well, thank you so much, Adrian. That was a great introduction to these two resources.